is Rob Reynolds, and welcome to College Algebra. Today we're going to be discussing section 3.3, looking at some different properties of some functions. But before I dive in, if you're in my online class or my face-to-face class, the schedule is the same. Just want to remind you that everything that we did this week is due next Wednesday. Of course, this was due before the test, but section 3.1 and 3.2 will be due midnight on the 11th, and then everything that we do this week will be due on the following 18th. On Wednesday again, we've got this My Math Lab, which I'll probably release here on the 17th. And just a little heads up, we have our next Blackboard test for my online students, and the face-to-face in-class test will be on the 20th. So a little scheduling. Please keep up with the calendar. No surprises. Today we're going to talk about even and odd functions. Even functions are just that. Y equals x squared, x to the fourth, x to the sixth. All of those are even, but the important thing is you need to know about even functions. They have symmetry about the y-axis. Odd functions have symmetry not about an axis, but about the origin. An odd function says every x and y goes to negative x and negative y. So sometimes I call it the 3-O rule. Odd functions are opposite, and they have symmetry about the origin. So I call that the 3L rule, or excuse me, the 3O rule. And even functions say every time you see an x, replace it with negative x, and you get the exact same y value back. So if you plug in a negative x, you still get y. Remember, y is defined as f of x. So if you replace x with a negative x, you get the exact same function back. You get the same y value back. So here's the definitions formally. An even function has symmetry about the y-axis, and if you replace x with negative x, then you get the same function. In my notes, it would look like this. An even function replaces x with negative x, and if that happens and you get the same y value, then we say that that's an even function. An odd function, I'm going to replace x with negative x, but look what happens. You get the opposite. So in my notes, I would have, if you replace x with negative x, you'll get the opposite of the function. That means that it's an odd function. And I have symmetry about the origin. So again, even functions have symmetry with respect to the y-axis, and y equals x squared is probably the most common function, but you can see I can flip that over. Be careful, odd functions do not have symmetry about the x-axis. Odd functions have symmetry about the origin. And again, what that means is all of your x's and y's go to negative x and negative y. It flips over the x and the y. That's what symmetry about the origin means. Here's some examples. This looks like it has symmetry about the y-axis, so I would say that's an even function. This is a big neither. It doesn't have symmetry about the x or the y. And it looks like every point here, x and y, goes to negative x and negative y. So I would say this is a good example of an odd function. So trying to identify even and odd, if I don't give you a graph, says every time you see an x, let's replace it with negative x. If it's the same, then it's even. If it's opposite, then it's odd. So let's plug in a negative x and try to determine if it's the same or not. So this becomes x squared minus 5. It looks like it's the exact same function, and because it's the same, I would say even. Over here, it looks like this is going to be an odd function because I've got an x cubed for part B, but if we work it out, if I replace every x with negative x, we'll see that it's not odd because the negative 1 does not change. In order for it to be odd, I would have to have the exact opposite. And the opposite of x cubed minus 1 is actually negating not only x cubed, but it's also taking the opposite of negative 1, which is positive 1. So this is not opposite, and so I would probably say that this is a big neither. So this first one was, I think, even. Part B was a neither. Let's try part C. Part C says replace x with negative x. And I'm looking to see if it's the same or opposite. So I have negative 5x cubed plus x, that looks like it's the exact opposite because my negative x changes to positive x, and I started with a positive and I end up with a negative. So they've distributed the negative, but certainly that is opposite. The last one, I recognize this as the absolute value function. I know that has symmetry, so therefore it's even. Remember, if you place x with negative x and take the absolute value of negative x, you get the same function. So next we're going to talk about intervals of increase and decrease and constant functions. So you can see I've highlighted here the interval that it's increasing on. When I ask for intervals of increase, I only want x's, the x values. So the x value that it starts increasing, it looks like it starts increasing here on this x value. So starting at -2, I begin my increase. And it looks like it ends at increase. It ends at the x value of 0. So again, I'm going from this value, which is -4, all the way up to 0. And in this interval, those are my x intervals, I would say it's increasing between -4 and 0. You can write it in inequality notation, or hopefully you're getting more and more used to interval notation. I really prefer interval. That's what they probably use for calculus more often. So in this one, intervals of decrease, again, I'm only looking at the x value. So I would say between -6 and -4, and it's also decreasing from this x value 3 to 6. So I would have a couple intervals of decrease, and I would list them both either with a union sign or separating them with a comma on my math lab. The constant function just means where it's horizontal. Again, x values, I'm only giving x values for the constant function between 0 and 3. Don't look at the y values when you tell me intervals of increase and decrease. So if the function starts low and then it gets higher, then that's going to be increasing. So this is the y value. If the y value starts, this is the y value at x of 1, this is the y value at x of 2. If it starts low and gets high, then it's increasing. But it's kind of confusing because they use a less than sign here. One student told me that they can look at this right here, a little memory aid hook, and this looks like intervals of increase because this is going up. This is a less than bar, but the top of it is decreasing. And so they can remember that the function, because sometimes it's confusing when you see that the f at x is greater than. Usually great means you're going up. But in this case, greater than means the function is decreasing because it starts at great and then it goes to a lower function. So that means that the function is decreasing. And if they're equal, then we say that it's a constant function. So next we're going to look at finding maxes and mins, and local maxes and mins. So there is a local max. It's between some a value and b value. And here comes a local min. Again, somewhere between A and B, we have some point C between A and B that we have the lowest point of the function. Here are some definitions if you're reading. So if I ask at what value, I'm asking what x values, does it have a local? Now the actual maximum of this function is positive infinity. I know it goes up, but locally, I'm asking for a maximum, the highest point. So locally, between what, -2 and 3, looks like I have a local max at x equals 1. So, because this is the highest point between this interval a and b. And then so if I ask what is the local max, you'd probably tell me the ordered pair, 1, 2, or you could tell me in function notation, at f at 1, the y value would be 2. So there's a couple different ways you could denote this means 1, 2, because it is f of x equaling the y. For this one, we're going to find the minimum. It looks like I have 2 local mins. The actual minimum is this point, 3, 0, but a local means I might have more than one. So I would say there's a local min at -1, and there's also a local min at 3. If I ask what they are, I would say -1, 1 is a minimum, and there's another minimum at 3, 0. You can always write that in function notation. There's one of them, -1, 1, and here comes the other one, 3, 0. So once I find the local max and the mins, then I can talk about intervals of increase and decrease. So it looks like in pink, I'm finding intervals of increase. So again, I'm going to tell you the x values between, looks like between -1 and 1, the function is increasing. Then looks like it's increasing as well over here. And I would denote that as everything from 3 to infinity. And again, you can put a comma or a union sign in between that. Intervals of decrease would be here in blue, so, here in blue. So it looks like it starts from negative infinity and goes up to the x value of -1. And that's in union with, looks like it's decreasing here, the x value is 1, and it stops decreasing at the x value 3. So remember, intervals of increase and decrease are only interested in the x values. So here are some answers. It looks like we did pretty good. Pull out your graphing calculators, and I'll show you how to find intervals of increase and decrease maxes and mins by using your graphing calculators. So we're going to type in this function. If you turn on your graphing calculators, I'm going to type in 2x cubed minus 3x plus 1. I'm going to hit zoom 6. That's going to give me a 10 by 10 by 10 graph, and I'm not really interested in the 10 by 10 because it says I'm only interested in the local maxes and mins between -2 and 2. I can see them pretty good. If you wanted to zoom in here, you could, or you could go under your window and just look 5 units to the left and 5 units to the right. And this will take me in a little bit closer so I can see maxes and mins. To find maxes and mins, I hit second trace, which is a calculate key. Let's go for the local max first of all, which is number 4. And then it says your left bound, guess to the left. So either you could scroll over here by continuing clicking, or you can hold it down a little bit faster and a little less annoying so you don't have to hear all those clicks. So guess left, guess right, and then it says guess on. So there is maximum. And it looks like, I think that's the only maximum of this particular function. Let's try that again, but this time let's go for the minimum. So I'm hitting second trace. This time I'm going to hit the number 3 to find the minimum. I'm going to guess left, which it looks like it is. I'm going to guess to the right. So again, I'll hold down the blue arrow. Guess to the right, anywhere to the right. So I know it's above. I don't care if it's above or below. Just make sure that that bug is to the right. Press enter and then back up and guess on. And so here is a minimum. Now once I have my local maxes and mins, it's pretty easy. I don't think it captured that. It's pretty easy then to find intervals of increase and decrease. So let's see if I can do that. There's my max. Let's put the max and the min on the same slide so we can see what's going on here. Alright, so then the next thing they're going to do after you find maxes and mins, so here's a nice max, here's my minimum, then I can start talking about intervals of increase. And it looks like it's increasing all the way up to that max. So I would say the x value, which starts at negative infinity, I don't care about how far down it goes, I'm looking about how far to the left it goes. And it goes from negative infinity up to that point, which we've found on our calculator is negative 0.707. And it also looks like it's increasing from here to here, but I'll look over here so I can find that x value, which is a 0.707 to infinity. Those are intervals of increase. It looks like the only intervals of decrease are between the max and the min. And we found the max to be negative 0.707, and we found the minimum, right at this point, the x value, don't worry about the y's, to be 707. So again, that's how to find maxes and mins, intervals of increase and decrease on your graphing calculator. Here's another example which you can practice, which I'm not going to spend the time to. This one's a little bit harder. I will show you, maybe I should do a little bit of this, because sometimes it's hard to find the window or the proper window setup. And I think that's why I had this example. So 2x cubed minus 3x plus 1. Sometimes people try zoom 6, because if I messed up my window from before, this will always give me a standard 10 by 10 by 10. Oh, no. That's the same problem. That's intervals of increase and decrease. Here's the problem I wanted. Let's try this again. 8x to the 4th minus 9x squared plus 3x minus 25. You can use your graphing calculators on your test. I'll assume that you're finding precise answers. I don't know how to do this without a graphing calculator. Well, actually I do. You don't want to know how to do this without a calculator, so go buy a calculator before you take the next next test. You can see, I know my general shape of an x to the fourth function should be a quadratic. Usually x to the fourth functions look kind of like a W. Sometimes it's like a U, but sometimes like a W. So I might not be seeing the whole function here. So I'm going to go, if I hit zoom 0, I kind of get a mess. Zoom 0 is a zoom fit. It's trying to locate the function, and I don't really get a good picture or a good image of what's going on here. So I'm going to go back to zoom 6. Sometimes zoom 0 works great. I'm not a big fan of zoom 0. I know that I need to see lower because I can see that the function's going down there. So I'm just going to guess my y-min needs to be a lot lower. So I'll guess negative 100. If that's not right, then I'll try 1,000 or 10,000. I'm going to hit trace, and oh, I can see the function pretty good. If I hit trace and then zoom to enter, I'm zooming in on that minimum. And that's a really good picture. I don't know what it looks like there's my window. Somewhere between negative 40 and negative 10. Looks to be pretty good. You could have just changed this to negative 3 and 3 if you like. But that's a pretty good viewing window. Once you have your viewing window, or a proper viewing window, you can hit second calculate, go find your minimum, guess to the left, guess to the right, guess on. I'll do one of them here. Press enter. Alright, and you could find the rest of them by yourself. There's one of the minimums. You'd have to find another minimum over here, and then you repeat the process for a maximum. The average rate of change is the last part of this section. Average rate of change definition is really just the slope of the line. So you have a function, and the average rate of change is the slope on average for that function. And slope is defined as y minus y over x minus x, or f of b minus f of a. Remember, those are y values over x minus a. Let's go second minus the first. Let's go f of b minus f of a. Yeah, over b minus a. So there's my average rate of change definition. I might have it on here on the next slide. There it is. They did f of b, f at x. I would say f at b minus f at a all over b minus a is the definition that they use in calculus. We might as well use that here as well. So here we go. To find the average rate of change between 1 to 3, finding just this slope. It's not linear, but it's on average what it is. So it's f of 3 minus f at 1 over 3 minus 1. So f at 3 says let x be 3. So 3 squared is 9 times 3 is 27. So I would say 27 minus f at 1 would just be a 3 over 2. So that gives me, what, 24 halves or a whopping 12. Let's repeat the process one more time. I'll try this one. For part B, I would do f at 5 minus f at 1, all divided by 5 minus 1. So f at 5 would be 5 squared or 25. 25 times 3 is 75. So 75 minus f at 1, we already found out that f at 1 is a 3, all over 4. And you could simplify that and get, good, 72 divided by 4 right here, which reduces to 18. And if you'd like to try part C, there's the correct answer for it. So again, this is just the secant line. It's the slope of this line. And later on in calculus, you're going to push that secant line to the limit, and you'll get the tangent line, which is the definition of the derivative, which you'll get to in calculus. So the last thing I want to talk to you about is how do you find the equation of the secant line. And remember, that's just the line, y equals mx plus b, and you need two things. You need a point, which it looks like we have, negative 2, this is a y value, so I can evaluate f at negative 2. Let's do that real quick. 2 squared is 4 times 3, which is 12. Negative 2 times negative 2 is plus 4, plus 3 more, and that's going to be 19. So I know I've got a point already. All I need to do is find slope, and fortunately for us, we just got the directions to say, hey, let's go find slope by doing f of b, this is my b, minus f at a, or in this case, f at x minus f at negative 2 all over x minus a negative 2. So f at x is really just the function. So I'm going to just replace the function here, 3x squared minus 2x plus 3. I'm going to subtract off the function evaluated at negative 2. So it says subtract off a 19, because I've already evaluated that. All over, this comes x plus 2. So if I simplify this, this is really just 3x squared minus 2x, and this is a minus 16, all divided by x plus 2. So this is interesting because I think this factors, and I think one of the factors is an x plus 2, so you can cancel it. If that's true, this has got to be a 3x and an 8, because the 8 times 2 is the 16. We can check it. Signs are going to be different. The larger term is negative. So 6 and 8, they differ by 2, which is I wanted. The larger term is negative. That does cancel. So I could say this is the general equation of the secant line at any point. And if you want to evaluate it or find the results from negative 2 to 1, you could just find f at 1 and say 3 times 1 minus 8 would be 3 minus 8 or negative 5. So there's a lot of different ways that you could find this answer. The book is showing you their solution underneath this beach scene. They just did it directly. They did the f at 1. We did f at x here. The author here just did f at 1 minus f at negative 2 for part B. You could have just taken this 1 though and plugged it into our definition or our formula. The last part in part C just says find the equation of that line. And again, we've got everything that we need. We found out that the slope, the average rate of change at that point at 1 is negative 5. So we've got a good slope here. The slope is negative 5. And we've got a point, which was negative 2. And remember, g at negative 2, I believe, turned out to be 19. So we've got everything we need. We've got our y value to be 19. We have our slope to be negative 5. The x value is negative 2. And all I need to do is subtract off 10 from both sides to come up with the y-intercept of 9. Now that I have the y-intercept and slope, I can write a nice equation of the secant line, which would be y is equal to negative 5x plus 9. I hope you found this helpful. There's how the author works it out. If you have questions, again, there's a nice graph and representation of the average rate of change. If you have any questions, please feel free to email me.